Hello everyone, welcome back to Turning Turing. In this video, we'll try to understand selection sort algorithm step by step. We'll try to understand the concept, apply that concept on an example, and then discuss the code for the algorithm. We'll also discuss the time and space complexity and the pros and cons of this algorithm. So basically, selection sort works by repeatedly selecting the smallest element from the unsorted portion of the array and moving it to its correct position. Let's say that we are given an array and we divide the array into two parts, sorted and unsorted. When we start, the entire array is unsorted. So size of unsorted part is n, which is length of the array, and sorted part is 0. Now find the smallest element in the unsorted part and swap it with the first element of the unsorted part. So right now the entire array is unsorted. We'll find the smallest element. Let's say that this is the smallest element. So we'll swap it with the first element of the unsorted part. So this will be swapped with this, and let's say whatever was here will come here. Because this entire array was unsorted at the starting and this is the smallest element, so it will be swapped with the first element of the unsorted array. Now what will happen? The array will look something like this, and the first element of the unsorted array is going to come here and the smallest element is going to come here. Now this will become sorted and the remaining part is still the unsorted part. Now we repeatedly do this same thing over and over. So again, from the unsorted part, which is this, we'll select the smallest element. Let's say that this is the smallest element. We'll swap it with the first element of the unsorted part. So let's say this is the first element of the unsorted array. We'll swap it with the smallest element of the remaining array. So again, this element is going to come here and this is going to become sorted. This part is going to become sorted and the remaining part, this is going to be unsorted. So at first the sorted array will be of size 0, unsorted array will be 0 to n minus 1. Then sorted will be size 1, which is index 0, and unsorted will be 1 to n minus 1. Then sorted will be of size 2, 0 to index 1, and unsorted will be from index 2 to index n minus 1. So on till the entire array is sorted. Selection sort is easy to implement and works well for small data sets. So let's try it out on a small example. Let's say that initially we are given an array 64, 25, 12, 22 and 11. Now as we know, initially we assume that the entire array is unsorted. Now in this unsorted array, we'll find the smallest element and swap it with the first element of the unsorted array. So the smallest element is 11 and the first element of unsorted array is 64. So we'll swap these two. So our array would look something like 11, 25, 12, 22 and 64. Now we say that this is a sorted array and the remaining array is unsorted array. Now we'll repeat the above step for the unsorted part. Now we'll find the smallest element in the unsorted part again, which is 12, and the first element of the unsorted part, which is 25. Now we'll swap both these two and the new array will be 11, 12, 25, 22, 64. Now we say that this is going to be sorted and the remaining part is the unsorted part. Again repeat the same, 22 smallest element, first element 25, swap these two. So the new array will be 11, 12, 25 and 22 will be swapped. So it will be 22, 25, 64. You can easily see that how selection sort is giving us a sorted array. Now the unsorted part is this and sorted part is this. So the smallest element is 25, which is also the first element. So no swap happens. The array remains the same. And since now the size of the sorted array has become n minus 1, we'll stop our selection sort algorithm and this is our final sorted array. And as you can see, it is actually sorted in ascending order. So now we'll quickly move on to the code for selection sort algorithm, and here is how you implement selection sort. So we've defined our method, which is selection sort, and we've been given an array. So here our array is basically a vector of integers which we need to sort, and n is the size of this array given. So as we know that initially our unsorted array is from 0 to n minus 1. So our entire array is actually unsorted. So first what we do is we find the smallest element in our unsorted part. Now this is the algorithm for finding the smallest element in the unsorted part. We have basically assumed that the first index is the smallest element, and then we iterate over through the remaining elements. If we find another element which is smaller than the current min element, we just update the min index. And after this step, we'll have the smallest element with us. Now once we have the smallest element, what we have to do is swap the smallest element with the first element of the unsorted array. Now here basically we are swapping it with the first element. So I is basically representing the start of the unsorted array. So I is basically the first element, or we have stored the index for the smallest element in min index. We swap these two, and then we move on to the next step. So coming to the time complexity of selection sort, we can see that there are two loop of size n. So it very easily we can say that the time complexity is big O n square. But let's try to see it in a better way, or let's try to come up with the time complexity in a more intuitive way. So in the first step, when the entire array is unsorted, we'll be doing n minus 1 comparisons or n minus 1 operations, because we would be comparing the numbers n minus 1 times to find the smallest element. So in the first step, there are n minus 1 comparisons. In the next step, when the size of the unsorted array decreases by 1, we'll be doing n minus 2 comparisons to find the smallest element. So the next step, there will be n minus 2. Then again the unsorted array will decrease by 1, and so on and so forth until the size of the unsorted array is 2, where we'll only have one comparison. So these are the total number of comparisons that we are going to do in our algorithm, and we know that the sum for this is basically n minus 1 into n by 2. So we can see that the number of comparisons we are going to do is going to be of the order of n square, and hence we can say that the time complexity for selection sort is basically big O of n square. Selection sort is an in-place algorithm, so we do not require any additional space. And you have also seen in our code also we are not using any helper space. We are using the same given array for swapping the elements, and therefore the space complexity for selection sort is big O of 1. So although time complexity big O of n square isn't ideal for large data sets, selection sort is efficient for small arrays or when simplicity is preferred. So coming to the pros and cons of selection sort, again as I mentioned, it is very intuitive and simple algorithm. It is very easy to implement as well. It requires no additional memory. It's an in-place algorithm, and it performs minimal number of swaps as compared to other algorithms. So you can see that in bubble sort we were constantly swapping the adjacent elements. In insertion sort also you'll see that when we have to place the element in its correct position, we'll have to do a large number of swaps. Here only we are doing one swap per step, where we are swapping the first element of the unsorted array and the smallest element. Now coming to the cons of selection sort, again inefficient for large data sets due to big O of n square time complexity, and it always scans the entire unsorted portion even if the array is already sorted. So we do not have bubble sort like optimization, where if the remaining array is sorted, we just end our program and return whatever array we have. If you found this explanation helpful, give this video a like and subscribe for more coding tutorials. Got questions or feedback? Drop them in the comments below. Thanks for watching and happy coding. Bye bye.